this video, we're going to talk about inverse variation and the graphs of inverse variation. So, the graph of inverse variation, which can be represented as y equals 1 over x, looks like this, where if this is your quadrant, you have a kind of really wide U and another really wide U here and here, diagonally across from each other. Each part of this is called a branch. To talk about the characteristics of an inverse variation graph, the domain would be all real numbers except for 0. Notice that it doesn't touch the 0. The range is also all real numbers except for 0. Keeping in mind, your x values would be here and here. Your y values would be here and here. Your asymptotes, remember, asymptote is where it approaches 0. So asymptotes are really easy to see on an inverse variation graph. If we look at this graph, you'll notice that it comes really close to my x and y axis, but it never actually touches it. So in this case, we would say that the x-axis and the y-axis are our asymptotes. Asymptote is just the line that it approaches, the 0 line. Since there are restrictions at 0, we can say that x and y-axis are our asymptotes. The more we work with them, the more clear asymptote will become. Intercepts, on this graph there are no intercepts because it's never going to actually touch, it's never going to cross the axis. Now, we can say there's a point here and a point here. They're not actually called an intercept, so to speak. So let's find out some more information about inverse variation. A whole lot of information. So the inverse variation function is written in the form y equals k over x. This is just the generic form, where k, which is going to be a number, is never 0, and x, which is the variable, is never 0. So y equals k over x. Remember on the slide before this, I had it written as y equals 1 over x. I had just substituted in a 1 for that k. The k is called the constant of variation. So that means that no matter what I change my x to, meaning that variable, that k is always going to stay the same. And sometimes when we work with inverse variation, we're solving to find our constant of variation and then we're plugging it into something else. But as far as our generic goes, the k is called the constant of variation. In inverse variation functions, the x variable increases as the y variable decreases, and it goes the opposite as well. But if I increase this on the bottom, obviously this is going to decrease. And that's because of this k. But this k is going to stay the same, and every time I increase this number, this is going to get smaller. If k is positive, the branches are going to be in quadrants 1 and 3, or they're going to be here and here. That's when this top number is positive. If k is negative, the branches will be in quadrants 2 and 4. In other words, your graph will look like this. So if your top number is positive, or if your entire equation is positive, I should say, your graph will look like this. If it's negative, your graph will look like that. Okay? Transforming inverse variation. So here's our generic equation when it's transformed. Y equals negative a over x minus c plus d. And sometimes we could change that a to a k, but a is what we've seen on other equations, so I put it back as a. Now, what do they all mean? Well, that negative tells us vertical reflection, just like it has in every other equation. The a tells us vertical stretch if a is greater than 1, which makes it more narrow, or vertical compression, which makes it more flat, if a is greater than 0 and less than 1. It makes it flatter. Meaning that it's a fraction. This rule is the same that it has been for every other type of function that we've dealt with. This c moves it left or right, and this d moves it up or down. The c and d rules are the same that they have been. The c is just like it's been in equations where if it were inside of parentheses, and the d is like it has been if it's outside of parentheses. It's just in a slightly different format now. This a over x, we've just now, instead of putting it in parentheses, it's on the bottom. Now, also the c represents our vertical asymptote, and the d represents your horizontal asymptote. A just tells you how stretched or compressed the graph is going to be. So the rules for transforming an inverse variation function are the same as they are for everything, except for instead of being in parentheses, it's on the bottom to tell you if it goes left or right. And again, negative is going to mean it goes right, whereas positive goes left. On the outside tells you up or down, and plus means up, negative means down. Okay, a little more information and then we're actually going to graph some. So for inverse variation functions, the A tells us how far the branches stretch from the asymptote. In other words, the A kind of tells you when you graph, are you really, really close or are you far out? So that A tells you where is your point. This point's called a corner. That's what the A is going to tell you. So while we don't have intercepts, we do have corners. So we use this value to help us find the corner point. Specifically, we take the square root of K, or A, to find the corner. And remember, I told you that we could write the equation as K over X minus C, because remember our original equation is this, or A over X minus C. And again, I put the A because that's what it's been in every other equation. But remember, if this is your generic inverse variation formula, then when we start transforming it, we do minus C and plus D, or we flip it. So in order to find out how far away from our axes we're going to be, we're looking for something called a corner point. All right, so let's do some examples. Let's do some graphing, and let's practice writing an actual equation. So here we go. Let's graph this one. So first of all, let's figure out which two quadrants it's in. Is it in 1 and 3 or 2 and 4? Well, it's not negative, so it's going to be in quadrants. It's going to be in quadrants 1 and 3. Since it's not negative, it goes here and here. Then I notice that my A or my K value is 1. So to find my corners, I'm going to take the square root of 1, which equals 1. So that means when I go to put it on there, it's just barely going to be off of my asymptotes. Now, what are my asymptotes? Remember, this one tells us our vertical asymptote. So our vertical, I'm just going to write VA. VA is going to be at positive 3, and my horizontal asymptote is going to be at positive 4. Because remember, this value, which was your C value, represents your vertical. D value represents your horizontal. So vertical, up and down, is coming over here. So 1, 2, 3. Here's my vertical asymptote. Whoops, I missed it, but that's okay. Horizontal, 1, 2, 3, 4. It's going up here. I'm going to erase this now because I need that space. Actually, I'm erasing all of this. Okay. I'll rewrite it down here just so we have it. My corners are at 1, and I know it's in quadrants 1 and 3. 3. Okay. So if my corners are at plus 1, I'm going to come out just a little bit and put a dot. Come out just a little bit and put a dot. Remember, quadrants 1 and 3. So now when I go to draw, I'm going to come down really close because I want it to get closer and closer, but I don't want it to touch. Whoops, that one touched. Okay, so it's 1 and 3, really close to my asymptote, but not quite touching. Okay, so now let's look at this one, okay? It is negative, so this one's going to quadrant 2 and 4, so it's got to go here and here. I have a vertical asymptote of -1. My horizontal asymptote it doesn't have anything out here, so it's just going to be my x-axis. X-axis. Okay? And then I've got to look up here at my a value or my k value. Square root of that is 2. So I'm going to want to go 2 out, 2 out. So let's get our vertical asymptote drawn at -1. My horizontal asymptote drawn right there. Now 2 out, so 1, 2, 1, 2. Okay, so you'll notice this one is a little further out from my asymptote because the corner points are farther. And I had to make sure it was in quadrants 2 and 4. So that is how you draw an inverse variation graph based on the equation. So now, what if I want to write an inverse variation function that has asymptotes at -4 and 5, but has branches in quadrants 2 and 4? Okay, so we know we need y equals, okay, branches in quadrants 2 and 4, that means negative. Okay, it doesn't tell me it has corner pockets that are backed up, so that means it's going to have a 1. Okay, our x value is -4, so that means we go opposite, x plus 4. And then y value of +5, so +5. So this would be our equation that represents what this says. And that's how you graph and write functions in inverse variation.